In science, we're all about quantifying things, giving a number to things. And I give these guys credit, although they kind of messed us up for years to come. But back in the BC times, a budding scientist actually, I like to picture him as laying down on a blanket. I'm sure he didn't, but looked up at the nighttime sky and he identified the dimmest star he could see, +6. So +6, dimmest. And the brightest star he could see, a +1. So do you see what I mean? We already have and we have stuck with this scale. So +1 is bright, +6 is dim. And so of course since that time we have seen things even dimmer and we have seen things even brighter. So we have expanded that scale. And it's called the apparent brightness scale. So lest you think that there's not much difference in a +1 and a +6, there's a big difference because each one division you jump up, it is actually a factor of 10 with regard to its apparent brightness. So +1 and +6 are very different. So I'm going to show you here a scale then of how that would work. Now these are apparent brightnesses. Okay, so it's a lowercase m, it's apparent brightness, and we use, like I said, a lowercase m. We're going to use an uppercase M for something else. So how bright does the sun appear to us? Well, no duh, okay? It's very bright, the sun is to us because of its proximity to us. We love the sun. But it's a -26.7. That's very bright. A full moon, -12.6. Okay, less bright than that, although pretty bright in the nighttime sky. Venus, -4.4. Sirius, -1.44. Naked eye limit. Now that's without binoculars and dark skies. We get kind of like the same +6 that they got. Using binoculars, you're gathering those photons and concentrating them so you can see something as dim as a +10. Pluto, though, you could not see through your binoculars anyway because it's a +15.5. The Hubble Space Telescope, though, is awesome in orbit about the Earth. It actually can gather photons and make sense of objects with just an apparent magnitude of +30. So that actually is the magnitude scale. Now that's apparent magnitude. I want to introduce you to one other magnitude scale, and it's called absolute brightness, or the absolute magnitude. And notice it is a capital M instead of a lowercase m. So absolute brightness actually is a little, can in some cases for scientists make a little more sense, because absolute brightness then actually removes the factor of proximity of the object. So as you know intuitively, what we have in here is a candle. Okay, intuitively you know that as you get out farther and farther from that candle, okay, actually it's going to be dimmer out here than it is here. And so this is brighter in here. So there's something called the inverse square law, and as it turns out, as your distance doubles, okay, you're actually the area over which that same shaft of light is going to be distributed quadruples. So it's what we call an inverse square relationship. Bottom line is sometimes stars are bright in the nighttime sky, not because they're pumping out a lot of energy, which might be significant to the chemistry that's going on, but just because they're relatively close. So what scientists do then to kind of what we say normalize for distance is and it's kind of a thought process. We cannot do this, but we can actually mathematically do this. Theoretically place the object 10 parsecs from us. Remember, parsec is 3.26 light years. So 10 parsecs from the Earth, and then they assign a new brightness value. And that brightness value is the same brightness scale as we use for apparent magnitude. So I have an example here. So a minute ago we said that the sun has an apparent magnitude of a whopping -26.7. That is crazy. That's very bright. Well, no kidding, right? But if we were to locate the sun, and I'm not in favor of it, 10 parsecs from the Earth and look at it again, it would be just kind of a moderately bright star. It would appear as a plus 4.9. So that's significantly dimmer if we place it 10 parsecs away. So, if we want to compare kind of the chemistry, we want to understand for the potential chemistry that's going on with a star, we have to use this kind of normalized brightness scale to compare stars with one another. And actually, we are going to be using this kind of normalized brightness scale coming up.